thanks for the invitation to speak and for the introduction. And yeah, I'm also maybe trying to correct. I'm trying not to give a not good talk, but we'll see how it's going to work out. Right? So I'm definitely not trying on purpose to mess up things. And to start with something which should be good because I stole it from Bernhard. I want to stress that there are aspects of rigidity in scalar curvature, and there are aspects of flexibility. I'm asked to find the fine line when we talk about rigidity, what setups we are going to focus on. And let me just write down one of these flexibility aspects, which is Lohkamp's result. This was 95, which says the matrix G on a smooth manifold M, such that the scalar curvature is bounded above by whatever constant. This is C0 dense in all metrics. And so we can impose certain things on scalar curvature without any trouble, and we get still almost every metric that way. So that's certainly flexibility. And of course, there's also the rigidity aspect, which I guess I could contribute to Kromov. 14, but also maybe Bamla 15. Which says that the metrics such as the scalar curvature is bounded below by some constant that is C0 closed. So pretty much the opposite of being dense. In particular, this explains one of our focal points. I mean that we restrict to scalar curvature positive or non-negative or bounded by some constant. Okay. Well, what should the rigidity be now? The mean today, in today's talks, more specifically, and the answer I want to give by a theorem, or by maybe a question, is the round metric special among PSC metrics on the sphere? And well, e.g. can be deformed, making scalar curvature. So we learned that its lower bounds, which are the rigid part, can be deformed, making scalar curvature even bigger. All of us know the answer. So maybe Bernhard or Rudi could give the answer. You cannot. So this was a question, right? A sub-question, and the answer is
you can
yes,
shrink
of course. Fun?
You can shrink it.
Yes, by shrinking. So we see that in the rigidity picture, it's not just the scalar curvature and maybe this lower bound of scalar curvature, which has to be taken into account, but this shrinking aspect also has to be taken into account. And now I want to state the first theorem, and that's a classical one. That's due to Llarull from, oops, no, I missed to write down the year, whatever, long time ago, which
98. It's 98.
98, great. So maybe because it's recorded, we add the 98 to it. If G on Sn satisfies the following things. The first thing is the scalar curvature control, and it just has to be bigger or equal to the scalar curvature of the round metric, which is n times n minus 1. And the second thing has to be this anti-shrinking control, and for that we just say that the length of every vector should be bigger or equal to the length for the standard Euclidean metric. Bigger or equal. Well, these two conditions imply that G is actually equal to the standard metric. So we have here PSC rigidity. Right, that's theorem A. But let me, and this is a kind of rigidity I guess we want to talk about. So under certain conditions, controlling scalar curvature and other things, the metric has to be the metric with which we compare, the rigid metric. We go to
maybe a very minor comment. I think the result was already proved in 88 in his thesis. Well, was somehow published in 98, which is
whatever. So even better. It's a classic result. We agree on that. Not so even more classic. It was 88. Let me stress that in the published version, maybe even in the thesis, Llarull managed to do a bit more. Namely, he actually got PSC rigidity. How do I write that? Permitting topology change. We can think of the theorem A as a theorem where we look at the identity map from the unknown metric G to the standard metric on the sphere. And our condition here just says that the identity map is a one Lipschitz map. And this I want to generalize, or this is what Llarull generalized, allowing different topologies even instead of the one on the sphere. So let F from M to Sn be a smooth map. Between these two Riemannian, closed Riemannian manifolds. So here we use the standard metric, and here we use some metric G as before. Well, again, we need the conditions we saw before. So the one condition was the metric control. So here we can say that the Lipschitz constant of f should be equal to 1, or we could say it is length non-increasing, then we need our control on the scalar curvature, which we could just formulate as before. The scalar curvature has to be bounded by the scalar curvature of the standard metric on the sphere. Well, and then eventually I want to conclude that this F is an isometry. So if you look at this, there is a very cheap way of getting the length control. If I don't add anything else, we could just take a constant map that's very length non-increasing. But of course, then we won't have any control on the metric G, and in particular, won't be able to disuse as F is an isometry. And to avoid that, I'm assuming here that the degree of F is non-zero. So I'm also assuming M orientable here. This, of course, well, prohibits F to be a constant map. It has to be surjective now. And now we have all the ingredients we might hope to need to get control the way I want it. Unfortunately, that's not quite true. Llarull proves his theorem under the additional assumption that M is a spin manifold. Because we will, so then the result is true, then F is an isometry, and that's precisely the rigidity where we permit topology change. We see in the end there is no topology change. M has to be the sphere, but a priori it could be a different manifold. And if you see M as a spin manifold, you already see what the methods are, which are used here. We are using the Dirac operator and index theory, and of course the Schrödinger and others formula. To control curvature. Okay, I'm going to talk maybe a tiny little bit about that in addition, but when one looks at these tools, one realizes it's really about curvature, curvature operator, and this means we're going to control, well, curvature is a concept which doesn't rely on lengths, but relies on two-dimensional objects, on planes in the tangent spaces, and that is why we can improve this from length non-increasing to a weaker condition, namely to the condition that the map is area non-increasing. This is implied by a von Lipschitz condition, but it is definitely strictly weaker. And so we see here a pattern. We have a tool which requires us to have an extra condition, but as a bonus, we also get a weakening of the initially kind of expected condition. Well, we're talking about curvatures, and that's why areas should suffice. So just a reminder, definition, such a map F is area non-increasing well, by definition, if and only if for every point, if you take the differential of F at that point. That's the map from the tangent space to the tangent space of the sphere at the image point. Well, this is a map between vector spaces with an inner product, between finite dimensional Euclidean vector spaces, and the Lipschitz 1 condition would be that this map has norm small equal to 1. Everything is, nothing is increased, everything is decreased. And the area condition is that we don't need to do this for lengths. We can go to the second exterior power and do that for, well, two-dimensional subspaces, essentially. So the norm of this, both left and right-hand side, from the Euclidean metric, from these Riemannian metrics have a norm. So the operator has a norm, and that has to be small equal to 1. And this is lambda 2 of the tangent space is some ingredient in the Schrödinger formula, which is used above. So if you look at this method part, I said I want to say a bit more about it. We actually look at a twisted Dirac operator, and we twist with the pullback of a nice bundle on the sphere, namely the spinor bundle. It has to be bundled, and it's a spinor bundle is in some sense a coincident. So it has to be bundled with interesting topology in it, which for the sphere, the spinor bundle does. And what Llarull and in all the business we then do is we compute explicitly the curvature. That requires to compute the curvature of the spinor bundle for the standard metric on the sphere. So you need something sufficiently nice that you can control it. And then you need to look at this pullback and see what the effect of the pullback is to get the curvature term in this Schrödinger formula. Schrödinger-Lichnerowitz formula. Well, what you also need is the topology plus an index theorem. Well, topology in our case is well, mainly that the degree of the map is non-zero and that we work with well understood manifolds like the sphere. I should say, I will say that in a second, we particularly work with the sphere in even dimension for this method. And then that has non-zero Euler characteristic, which is topology ingredient, which is needed to get a non-zero index, which corresponds to a harmonic spinor. Well, and then you put all these things together, the geometry conditions allow this harmonic spinor, which exists. So, only if, well, probably you will first see that the scalar curvature function for G and for the standard metric are the same, and then you will look even deeper into the formula and you will see that the differential, called it T earlier, I think, of F from the tangent space M to the tangent space of the sphere really has to be in isometry. for all x. And then finally, you use the inverse function theorem to derive from that the map has to be a Riemannian covering map. Of the sphere, so it's a sphere itself. So it's an isometry by itself. This is how the method works. Right. And one should say, well, to be honest, all newer results are based on refinements but there, as far as I know, there is not a really fundamentally different method which one has found to prove rigidity theorems of the kind we've just seen. In particular, there might be the first question one might ask here, can one use minimal hypersurfaces? I think there's some specific results here, kind of in larger generality. To get rigidity. And I think so far that's not known at all. Or am I here completely mistaken and I'm overlooking some interesting results? Could find the literature.
What exactly the question you're asking? In which generality? So in dimension 3, there is a kind of even finer result for rigidity with three-dimensional sphere, right? By Marcus and Neves.
Right, that doesn't really use minimal hypersurfaces, so that uses Ricci flow. So indeed.
No, it uses minimal surfaces. No, it uses surface index 1.
Okay.
It's much finer result, actually, unavailable by any other method. In dimension 3 specifically, right? It says that if a scalar curvature such and such, then it's swept over by small spheres, and it's by far more precise than any other result.
Okay, yeah.
Right.
So then I guess
then in dimension 4, wait. In dimension 4 also there is result for non-spin manifolds. Sphere, even with 2 punctures, are rigid. Right, for dimension 4. In high dimension, it's unclear, but still there are kind of results. So we can combine minimal surfaces and spin and zero operated. Pure by minimal surfaces you cannot get it, yeah, because of the problem with the area. Of course, nothing with area you cannot do by minimal surfaces except in dimension 3.
Yeah.
And by the way, in dimension 3, we also have an approach which goes back to Daniel Stern using harmonic maps.
Right.
And there is a kind of variation on that, which the authors call a space-time harmonic maps by Hirsch, Katsaras, Khoury, and Zhang. So they prove that the round sphere in dimension 3 is rigid. And they also have a version of the Llarull result under the additional assumption, some additional assumption of the second homology of the underlying manifold, so a comparison result, which is actually weaker than Llarull, but they use different methods.
But in dimension 3?
In dimension 3, yes.
So maybe my question to specify it so that it really remains open is if one is not in non-low dimensions. And low is typically by topologist standards 2, 3, 4. And then you would expect minimal hypersurface methods to also work in dimension 6. Very oops, I have to read that. Yeah, but that seems to be open and would be interesting. I think it would be interesting to get the Llarull result maybe with length control for the map, but without the spin condition, at least up to dimension 6 or 7. That's
now, concerning Llarull, I just want to make one message. So this was suggested by Blaine, yeah, exactly choosing this bundle and specifying the algebraic problem. So Blaine isolated the algebraic problem, computing spectrum of the curvature term for sphere, and this Llarull completed the computation right down. So essentially, it's at least half of this due to Blaine, yeah.
I guess that's right. I guess it was Llarull's PhD thesis with Lawson as the
yeah, but Llarull doesn't state it precisely, yeah. That's this scheme always suggested by Blaine, and the point of Llarull was actually furnish this computation, right? Which was set up by Blaine. He knew, of course, the answer.
So one should
Blaine
add
is fantastically good at computations.
One should add Lawson, I guess. Just
yeah, but Llarull now dead, so
the literature is yeah. The papers which are published are all published by Llarull. Lawson as the advisor.
Yeah, but again, you see, you cannot say it in public. It's private information. Yeah, so I can say it, but I wouldn't say it on paper. I mean, because there are many other, the more famous example is
as far as I understand, you're recording the lectures and posting them on the internet for the whole world to share for eternity, but that's happened now, right? Let's go a bit further.
Ising model, the most famous example is Ising model, which was suggested by his advisor. You never heard of Ising in any way in physics. He's done what his advisor, forgotten known physicist, told him to do, yeah. And this happens, but the name remains. The Llarull theorem doesn't mean he exactly 100% author of the theorem.
It makes it easier also because there's only one Llarull theorem. If you talk about the Lawson theorem, we might be confused because there are several. So at least
Lawson, the key idea, use the right bundle, of course.
Yeah. Was it B? I don't know. Or C. So those two guys, Götte and Semmelmann, took up the method and were kind of more efficient in computing curvature terms. So that is one of the tasks one has to do. One has to do by the explicit curvature computations. We just learned from Misha that this was a main contribution of Llarull to really work this out in detail and find it nicely in the paper. In local coordinates, one can be a bit more kind of systematic. This is what Götte and Semmelmann do, and they generalize to many more targets. I know X, G special. These are still special targets, so we need curvature operator non-negative. That restricts also the topology of the manifold X quite a bit. They also need a key Ricci curvature estimate. Which is just happening to show up in the rigidity computations. So the Ricci curvature has to be positive for the method to work, and it has to be dominated by the scalar curvature over 2 for the method to work. And then they conclude, so I'm a bit sloppy here, maybe F is a Riemannian covering again. And they ask a question. Let me take this. Is star enough for this topological change allowing scalar curvature rigidity? That might be, and it seems that again, if one looks at a literature which comes later, this key Ritchie estimate is always present. So that seems to be quite important to have. And let me make a remark here, which is also observed by Goethe and Semmelmann. Given any M which allows positive scalar curvature, there is a non-rigid PSC metric on M. So in general, it won't satisfy this key Ritchie estimate, of course, and that uses Lohkamp's flexibility result. So you can make so many PSC metrics by Lohkamp, but you can also make some which are definitely not going to be rigid, no matter with which manifold you start. Okay, but the general question is, of course, this is maybe the question of Goethe Semmelmann. The general question is which metrics, probably always of positive scalar curvature, are the rigid metrics, and maybe in particular the rigid metrics, even if we allow for topology change. So after this, time is really running.
Can I make another historical remark? Because in principle, the first computation, which implies rigidity of product of two spheres, is due already appears in the first paper by Hitchen, right? And from this follows rigidity of the scalar curvature on the product of spheres, two spheres, which is quite trivial already. And actually, in his computation, specifically the same as in Schrödinger paper. It's exactly with the line bundles, right? So I guess already it's written in Schrödinger, which implies, I haven't read the paper by Schrödinger, implies rigidity on the product of spheres.
Okay.
Modular index theorem. Of course, you have to check that the index theorem exactly gives the right index, but that's easiest case for compute, yeah. And then there is also intermediate paper by, of course, by Minou, who after Llarull, who proved it for rigidity of symmetric spaces, of Hermitian symmetric spaces, right? So they were kind of intermediate papers, yeah. Of course, this Goethe Semmelmann was kind of crucial, yeah, new step, yeah. But there were other people involved in history.
Sure, yeah. I mean, they also cite, of course, Minou on the other side. Yeah. I'm kind of focusing on some key...
But Minou was immediately kind of involved and just he kind of pinpointed the right points, yeah.
I have another question, actually. But I hoped so that this will be kept or can be kept short because I don't want to steal too much of the time. I find it hard to get a geometric intuition why it's the spinor bundle on the sphere, on the target sphere, which is exactly the correct twist bundle, so the pullback of this bundle. Apart from the computations that I know from Llarull, so that it exactly balances the other contribution from the spinor bundle on the domain. So is there any geometric intuition behind that? Why is the spinor bundle of the sphere is exactly the correct bundle that we have to use to get these results?
So one motivation, you remember, just I spoke to Blaine, yeah? And what he said immediately when I suggested this, actually, there must be regional. Oh, yeah, of course, he said, use spinor bundle, because Hopf bundle does it. And therefore, computation from Hopf bundle extends to the spin bundle. This was instantaneous reaction, yeah. And then Llarull wrote all this down. Yeah. So this I remember. I can nothing. It's invariant bundle, the only one having quadratic symmetry, and it's probably, if you really kind of use functorial language, it must follow from the what true for Hopf bundle. If this kind of picture, of course, was in mind of Blaine, and for him it was obvious kind of. Yeah. The Hopf bundle must go to the spin bundle. Yeah. You have to ask Blaine, of course. Yeah, him.
Sure.
Yeah. So for me, it was the story was finished, but then Llarull wrote the paper. Yeah, I mean,
so maybe here another remark, question. perhaps, well, I don't know. Yeah. What I wrote is so far mainly works for even dimensional manifolds. I mean, mainly works means this the Dirac operator method. Göttingen found a few cases where they can work with odd dimensional manifolds and some other index, some variants of the index which work there. And then Llarull uses some kind of suspension to go from odd spheres to even spheres. Maybe the question would be, can higher index be used more systematically to for odd dimensions to prove rigidity results beyond the few cases we know, which is odd dimensional spheres and a small class of the examples in the Göttingen world, and maybe a few more, but we saw the Hitchin result is a product of even dimensional spheres, so you don't see so many odd dimensional manifolds coming up there. Another question maybe is also, can one use more the suspension trick but the expense would be the manifolds become singular. Well, this is something Llarull avoided, and if you take the suspension of a sphere, you of course get a sphere again, which is not singular, at least not as a topological manifold. So I think this can be interesting questions which might generalize the scope where we can well, apply this method. I wanted, now I'm probably having just 5 more minutes, right?
Yeah, you have a little more until 50.
Okay, 6 more minutes, very good. That's a lot. More modern developments. I want to shortly mention the first one is manifolds with boundary, where we control the scalar curvature in the interior and the mean curvature of the boundary. And we have results by Lot, which uses Dirac operator with boundary conditions. And it turns out that in this comparison situation, one can, which is rare for the Dirac operator, use local boundary conditions, just like Dirichlet and Neumann boundary conditions, which make, of course, the local analysis and the geometry, connection geometry, kind of quite handleable. And this is maybe the main observation of Lot, that one really can apply these local boundary condition techniques, and then things go through. I don't cite the results exactly the way, because it would be too long to write them down. but I might also want to mention in this context results by Gromov, which was earlier than Lott, who uses doubling tricks. This is a bit tricky because you don't want to be in a situation where you can double and you get a smooth Riemannian manifold. So you use doubling plus some deformation of the metric to make it smooth again. And then you have to understand how much you can kind of undo this deformation. So you need some approximation results. That's also an interesting approach to work with manifolds with boundary. A third one, which is using, Dirac operator again, is by Cecchini and Zeidler. They use Dirac plus potential. So the potential function changes the index here a little bit, is the replacement for the boundary conditions. And again, there are very strong results they can obtain. They get exciting, somewhat unexpected rigidity results, even beyond the rigidity they have a comparison map. They just give conditions which says, with these conditions, the metric has to be precisely of this type, which I think is quite interesting. Maybe one should also mention Wang Xie Yu, which go beyond manifolds with boundaries to manifolds with corner. I think this has been discussed in a seminar, so I don't talk more about it now.
But was actually checked. Yeah, I think his last paper is still unchecked, right?
Right. It's interesting work. One still has to see when the final version will come out and what the final results then will precisely say, right? And the last 2 minutes I want to use for B, so maybe, which is low regularity of the comparison map F. If you think of what is going on, we said we have a condition on Lipschitz constant. So natural is to say just demand F to be one Lipschitz and not demand to be smooth, and still hope for the rigidity result that such a map has to be an isometry under the appropriate conditions. And if you're lowering the regularity for the map F, you might also lower the regularity of the metric G. We saw above that the scalar curvature world is strongly tied to C0 topologies. We might want to look at C0 metrics, or metrics which have maybe a little bit more than C0 regularity, where we can still make sense of curvature concept, in particular positive scalar curvature. There are also results. Here we have two kinds of methods, Li and Tan. That was very new. They use geometric flow, namely Ricci flow and for the metric, and harmonic map flow for the map, to pass to the smooth results, or reduce to the smooth results. This works for the flow for this von Lipschitz case. And then I'm also happy to mention work where I have contributed to. there is Simone Cecchini again, Bernhard Hanke, and myself, and I'm not sure whether this has also been discussed. We develop a low regularity Dirac method to treat this case. Actually, I should have done this in a different order because our work was done earlier. But this result, this method is really very exciting, and I think it's also something which has potential to be fruitfully applied in this low regularity context for other problems. Right, and there is for our work, there is a pitfall. The inverse function theorem is not a theorem in this low regularity Lipschitz map world. So you don't have it and you need a replacement. Which was a major obstacle in our work until we had found it using some what was it, conformal map techniques. Well, I think my time is more than over, so I will stop here. There is one result I haven't mentioned, which is also very recent, which is specific to dimension 4, that is by Betjol and Goodman. But I guess we have 60 more minutes to learn about that, so I had all the right not to mention it. But stay tuned. There is very recent specific 4-dimensional techniques we're going to learn about, I guess, how we get many more rigidity results of the kind we saw in dimension 4. So that's it for now.